Hello everyone, thank you for coming. I'm happy to have the chance to show our journey into Windows kernel streaming. I'm Angelboy. Currently, I'm working as a senior security researcher at DevCo, focusing on Windows vulnerability research. Today, I will be showing some new bug classes and new vulnerabilities in Windows kernel streaming. Last year, we found multiple vulnerabilities in kernel streaming during Pontoon. Most of them are outbound, along with parsing to kernel. I also present parsing to kernel at Cold last year. However, these dozens of vulnerabilities are just the tip of the iceberg. In fact, more and more vulnerabilities are streaming out, and many of them are exploitable. Let's quickly go through kernel streaming first. On Windows system, when you open the webcam or microphone, the system needs to read or write relay data such as your voice and capture imagery from your device into RAM. It is essential to read data into your computer more efficiently. Microsoft provides a framework called kernel streaming to handle this data. In kernel streaming, three multimedia class driver models are provided: port class, AV string, and the string class. Due to time constraint, we will not go into detail. If you want to interact with this device, like webcam on Windows, you need to open a device just like other device. For example, open a device and then use IOCTL to interact with it. Case also provides its own API to open the device. After we open this device, kernel will create some kernel stream relay instance, which are kernel streaming object. This instance will be frequently used, mainly to encapsulate the hardware functionalities for developers. Among them, the most important are case filter and the case pin. When we open an audio device, in most cases, it corresponds to a case filter, which is a green box in a diagram. The point for reading and writing data are called pins. If we want to read or write data, we must open a pin on the filter to create an instance to read from or write to the device. After that, we can use device IO control to interact with it. If you want to read from or write to the device, you also need to use IOCTL. After understanding of the functionalities of kernel streaming, we need to understand the architecture and how Windows implement it to find vulnerabilities. Following our analysis, the overall architecture looks like this diagram. After you send an IOCTL request to case device, these are the drivers that might handle your input. Let's talk about case sunk first. Case sunk is the entry point in kernel streaming. It converts 32-bit requests into 64-bit requests, allowing the underlying driver to handle the request without additional processing for 32-bit structure. Another one is case, which is one of the core components of kernel streaming. It is the kernel streaming library responsible for forwarding requests and handle function related to every string. We now have a basic understanding. Let's quickly review the vulnerability we discovered last year. The most important one was the parsing to kernel vulnerability. Kernel streaming has a feature that can resend IOCTL requests. We can use it as a proxy to bypass security check, relying in security vulnerability. For example, the vulnerability we used at Pontoon last year. The data provided by the user is directly used as a function call, leading to an arbitrary call. For more detail, you can refer to our blog. After we found parsing to kernel, we decided to dive into kernel streaming. Over the past year, we found more than 20 vulnerabilities. Most of them occur during frame handling. In this talk, we will focus on frame-related issues. Let's talk about kernel streaming frame. So what is kernel streaming frame? In kernel streaming, when reading data from a device, it will allocate case frame to store and describe the multimedia data. It also has a frame buffer to store the image data. MDO are used to measure this frame buffer, keeping track of their allocated physical memory, making data access much faster. So what is MDL? In the Windows kernel, MDL are mainly used to describe the physical memory mapping of a virtual address. In kernel streaming, an MDL describes a frame buffer that is mapped into user space and the kernel space. And both mapping refer to the same physical memory. As a result, when data is read from the device, it is written to both buffers at the same time. Now, let's talk about how application read data from a webcam and how case implement it. Here's a simple overview of the workflow of read stream from webcam. First, open the device to get a handle. Then create a pin on the filter and get a pin handle. After that, send an IOCTL to set the pin to run state. If a device is set to run state, you will see the webcam's light turn on, which means the camera is now ready. The next step is to use an IOCTL to read the frame from the pin into memory. When sending the IOCTL to read the stream, we need to provide a case string header structure as input to specify the necessary information. The most important fields are the data buffer and the buffer size. Case will map a frame buffer based on the buffer and the size you provide. You can also specify an option flag to indicate the attribute of the frame. Let's briefly introduce how case implement reading a frame. First, we need to allocate a buffer in user space to store the image data. Then we can pass the buffer's address and the size to the kernel using an IOCTL. After we send the IOCTL to webcam, it will process by KSUNC and the case. Once case receives the request, it passes the case string header, create an MDL accordingly, and insert it to the IRP. Next, the user buffer will be mapped into kernel space as the frame buffer according to the MDL. At this point, both the user buffer and the frame buffer point to the same physical memory. Finally, case allocate a case frame structure in kernel, which stores the MDL, the kernel frame buffer pointer, and the buffer size. Then the case frame is placed into the queue, waiting to be filled with the data. Next, the case worker pulls a case frame from the queue and begin capturing image data from the device into the corresponding frame buffer. By the way, we can request multiple frames at once, not just a single frame. Case will create an MDL chain according to case string header array. Finally, the corresponding case frames are placed into the queue in order. Each frame has one-to-one mapping with a string header, an MDL, and a case frame. Now, we have a basic understanding of the frame reading. Let's talk about the new bug classes we discovered during our research on kernel streaming. The first one is MDL cache buffer overflow. Before we move on, we need to talk about the MDL caching mechanism. In kernel stream, they add an MDL cache to speed up. You can enable it by setting option flag to 0x8000 or 10,000. It will use this mechanism to handle MDL and the frame buffer. The mechanism works by catching the frame buffer and its MDL after use, storing them in a list. When the same buffer is used again as an image buffer, the cache MDL are reused. I will walk you through this with some simple diagram. Suppose we send an IOCTL with the cache flag. In case, as mentioned earlier, it allocates an MDL and a mapper frame buffer. The difference here is that it also allocates an MDO cache entry, which record both the MDO and the user space image buffer. Next, it will allocate a cache frame structure and read data from the device. After handling the first IOCTL read request, the MDO entry is inserted into the MDO cache list. For subsequent requests, if the cache is enabled, a new frame buffer will not be allocated immediately. Instead, a smaller MDO is allocated as a temp MDO first. Next, it checks the MDO cache to see if there is a suitable MDO. It compares the user space buffer address, and if they match, the cache entry is taken out. And then the MDO in the original IRP is replaced with the cache 1. After that, this MDO is used to map the frame buffer, and the buffer is then used to receive the data from the device. But is it really safe? Something seems wrong here. In fact, when it looks up the suitable MDO from the MDO cache, it only compares the buffer address and does not check the size. This means that in the first request, we can provide a smaller frame buffer, and in the second request, reuse the same buffer address but specify a larger size. For example, in the first request, we ask for a frame buffer of size DOX1000. The kernel will allocate a DOX1000 frame buffer and read data into it. After complete the IOCTL request, the entry is inserted into the MDO cache. For the second request, we use the same buffer address but require a larger size. At this point, the MDO from the previous request is used again to map a frame buffer. It will also allocate a new cache frame. Then it stores the buffer size from cache header into the cache frame. When reading from the device, it will use the size in the cache frame. However, the buffer size is only DOX1000, while the data read from the device is much larger than the buffer. As a result, it leads to a buffer overflow. Among the vulnerabilities we discovered, 2 are related to this issue. The next bug class is MDO mismatch. When KSUNC receives a 32-bit request, it not only converts the request to 64-bit, but also pre-allocate an MDO for a frame buffer. As shown in this diagram, when we send a 32-bit request, KSUNC processes it first. KSUNC will set up the MDO and map the frame buffer. After that, it passes the IRP down to case. Since the MDO has already been created by KSUNC, case will not allocate a new one. Then it will allocate a case frame to handle the frame. Moreover, if we request multiple frames at once, KSUNC will pre-allocate all the necessary MDO and the frame buffer mapping. However, if the option flag is set to cache flag, the normal MDO allocation process will be skipped by KSUNC. That is, if the cache flag is set, KSUNC will not pre-allocate the MDO. Moreover, each frame is handled independently. When you submit multiple frames, it's possible to have just one cache. For example, suppose we submit 2 frames, and the second frame has a cache. KSUNC will handle it first. KSUNC will check the option flag for the first frame. If cache flag is not set, it will allocate an MDO and map the frame buffer. It then moves on to the second frame. Since the second frame has the cache flag, KSUNC will skip MDO allocation. After that, the IRP is passed down to case. Because the first frame doesn't have the cache flag, it assumes the MDO is ready and skip it. Then it moves on to the second frame. Since the second frame has the cache flag, case will allocate MDO and map the frame buffer. It then creates cache frame structure based on the order of cache string header entry. Each cache frame is paired one-to-one with its corresponding MDO. They are placed into the queue, waiting for the worker to pull them. But is it really safe? There seems to be something inconsistent. Let's build the MDO chain. Suppose we submit two frames. For the first one, we set the buffer size to 0x1000 and enable the cache flag. For the second one, we set the size to 0x20000, but we do not set the cache flag. K-Sun will check each header as usual. Because the first frame has the cache flag, it skips MDO allocation. Then it checks the second frame. Since the flag is not set, K-Sun will allocate MDO and map the frame buffer. Next, the IRP is passed down to case. At this point, case checks the option flag again. For the first frame, since it has the cache flag, it will allocate an MDO and map a frame buffer, and then insert it to the MDO chain. For the second one, the cache flag is not set. It will skip the allocation. Finally, case creates cache frame structure based on the MDO chain and the cache string header. The frame size from the header is stored into the corresponding cache frame for both frames. As shown in this diagram, the first frame will have a size of 0x1000 stored, while the second frame will have 0x20000 stored. Did you notice the problem? After we run it, we got BSOD. Why? The root cause of this issue is a mismatch between the cache string header and its corresponding MDO for each frame. For instance, the first cache string header might get paired with the MDO of the second frame, while the second cache string header gets linked to the MDO of the first frame. As you can see, each cache frame created by case is mapped to its corresponding MDO. When the worker copies data from the device, it uses the buffer and the size in each cache frame to perform copy operation. The second frame works the same way. The worker refers to the cache frame structure to determine where and how much data to copy. However, here's a problem. For a second cache frame, the actual buffer size is only 0x1000, but size in the cache frame is 0x20000. So when the worker uses the size during the copy operation, it attempts to copy 0x20000 byte into a small buffer. As a result, this leads to a buffer overflow. In fact, several of the vulnerabilities we discovered are related to this issue. If you can find a way to make the cache string header and MDO mismatch, you can easily trigger buffer overflow. The next bug class we are going to discuss is called the forgotten lock in MDO. It is a case of incorrect MDO handling. In fact, it is an unusual issue in MDO. Let's take a quick look at how MDO are typically used and some common mistakes that can happen around them. The MDO structure is defined as shown here. Start VA usually point to the original user space buffer. System VA is pointing to the kernel map virtual address. The PFN array at the end of the MDO contains the page frame number corresponding to the buffer. When the kernel needs to touch user memory, it often uses an MDO. Typically, kernel invokes this API shown in this diagram. First one is use IO allocate MDO to allocate MDO structure. It simply allocate an MDO structure based on the given virtual address and the length. The MDO will point to a buffer based on a parameter. In kernel streaming, this typically points to an image buffer in user space. Second, it needs to call pop and lock page with MDO to validate and lock the memory page. In this function, it will check if the buffer provided by user is valid according to the access mode flag, and then lock the corresponding physical page in memory. After that, it stores the corresponding PFN into the MDO. This looks just like this diagram. It fills in the PFN array at the end of MDO, and it also locks the page in the physical memory. Third, when the kernel needs to access the buffer, it will call map lock page specify cache. In this function, it will map a new virtual address using the PFN stored in the MDO. Just like the diagram, after use this function, it will use map a frame buffer in the kernel space. It will refer to the same physical address. The last step invoke unlock page and free MDO. This simply unlock the page and release the MDO. I will not go into detail here. Now, I will take a look at a few common vulnerabilities caused by incorrect MDO usage. The common issue we have been seeing recently. When the kernel use the pop and lock page API to map the memory address provided by user, it may incorrectly set access mode flag. This leads to the failure to check if the address belongs to user space. As a result, the user can do arbitrary memory writing in kernel space. There are many more overlooked issues out there. Even Microsoft driver security guidance example contains a mistake. In this document, Microsoft provides a secure example for map IO space. First, validate the physical address and use map IO space to map a virtual address. Then allocate an MDO for it. After that, call map lock page specify cache API to map the physical address to a virtual address. Now, you might notice something strange here. Where is pop and lock page? As we mentioned earlier, in typical usage, after allocate an MDO, you need to call pop and lock page or other API to lock the physical page. But in this case, the code called map lock page specify cache directly. This leads to undefined behavior. Here's a quick breakdown using diagram to explain what happened. First, IO allocate MDO is called to allocate the MDO structure and initialize some basic information. At this point, the PFN array in the MDO is uninitialized data. However, if we directly call map lock page specify cache to map memory, it will still attempt to reference the PFN inside the MDO. In many cases, this leads to a BSOD. This kind of mistake happens all over kernel streaming. Next, I will examine a vulnerability which clearly demonstrates this issue. We once again create two cache string headers. Both frames are of the same size. The first frame has a cache flag, while the second one does not. As mentioned earlier, CacheSync will allocate and lock the MDO for a frame that does not have the cache flag. Once that's done, the IRP is passed down to cache. Now, let's take a closer look at how cache handles this frame. If we look at the first while loop inside cache, you will see that it checks each cache string header to decide whether an MDO allocation is needed. If the cache flag is set, it will allocate a new MDO. But in our case, the first frame has the cache flag, and the second one does not. When cache begins processing the second frame, it will call cache pop stream IRP. At this point, the MDO chain inside the IRP looks like this. The first MDO is already locked, but the second one is not locked at all. Then cache pop string IRP handles the mapping of frame buffer. It will use map lock page specify cache to do it. If the MDO is marked as lock, the function map the memory directly, but there is a problem. It only checks the first MDO in the MDO chain and assumes that the entire chain has already been locked. When map lock page specified cache is used on the second MDO, it ends up mapping memory based on an unusualized PFN list. Does this only lead to a DOS? The good news is that the MDO allocated by IO allocate MDO is unusualized in non-page pool. That is, the content can be controlled by using a spreading technique. We can use namepipe to spread a large number of objects to fill memory with controlled data. When map lock page specified cache is called afterward, it will regard those control PFN as very physical page, and the map length as a frame buffer. Finally, when the worker copy image data from the device, it writes directly to the physical address we controlled. That is, we have an arbitrary physical memory write. The next step is to achieve EOP with arbitrary physical memory write. But where to write? Interestingly, when we test on 24H2, we noticed that the physical address of NT was always a fixed value in many environments. So does that mean we can just write directly to NT and take over the kernel? There's the problem. We cannot control the data coming from the webcam. At first, it looked like we were stuck, but luckily, kernel streaming offers an attribute called buffer mode. If buffer mode is enabled, Cache will allocate a new buffer as an intermediate buffer. It then copies the content from the original image buffer into the new buffer memory. Then we stop the streaming. Cache will copy the content from the buffer memory back into the frame buffer. However, this frame buffer has already been mapped to a physical address of NT image. In other words, we now have an arbitrary physical memory write with fully controlled data. This opens the door to directly modify kernel code to EOP. Okay, let me demo it. This exploit is running on 24H2 without leak, and I use a normal user to run the exploit, and spread the MDO, then get system. Okay, thanks. There are multiple ways to cause this issue in kernel streaming. As long as you find a way to make it forget lock page, it can result in an arbitrary physical memory writing. The last issue we would like to show is frame buffer misalignment. But before diving into that, we need to introduce a cache object in kernel streaming, the cache allocator. Through cache allocator, a set of frame buffer can be pre-allocated and reused, reducing the overhead of dynamic memory allocation during streaming. In general, you can create a cache allocator using the cache create allocator API, and configure it using a structure called cache allocator framing, such as the number of frame buffer and the size of each buffer. You can also specify the alignment for each frame buffer. In fact, we need to provide an alignment mask for it. For example, when a pin is open, the kernel will create a pin object. Then we can create a cache allocator and attach it to the pin. Before reading data from the pin, we need to set its state to run. At this moment, the allocator will pre-allocate the number of frame buffer we have set up. From that point on, data is streamed from the device into pre-allocated frame buffer. When we send an IOCTL to read the data, the process begins just like we described earlier. However, instead of reading from the device each time, the worker will copy the data from the pre-allocated frame buffer. Today, we will focus on how the default allocator measures pre-allocate buffer. When we call case create allocator, case create a default allocator and then initialize it using the parameter we provide. Internally, case implement its own allocation function. It also uses a lookup assign list to measure the buffer efficiently. The allocation function is quite simple. It just calls ex allocate pool to allocate memory. If an alignment mask is specified, case add a 4-byte value representing the padding size in front of the frame buffer. Then in a free routine, case use this padding size to calculate the original pointer returned by ex allocate pool. As shown in this diagram, the memory layout of the pool looks like this. The purple region represents the padding and the blue region is the frame buffer. The 4 bytes just before the frame buffer are used to store the padding size. Under normal case, the alignment mask should be a power of 2 minus 1. However, here's the problem. Case only check whether the alignment mask is greater than 0xFFF. That is, we can submit any value less than 0xFF. At first glance, this might seem like a useless bug, just a minor memory alignment issue. But what happens when that misalignment buffer meet the lookup assign list? Let's take a look at lookup assign list. Lookup assign lists are per processor cache for fixed size memory block. It uses a simple single linked list. Allocation and free always check the list first before using a general pool. That means when we allocate a frame buffer, it will be taken from the list. And when we release a frame buffer, it will be inserted back into the list. Another property is that lookup assign list entry must be 0x10 byte aligned. As you can see, before returning a chunk, the kernel aligns the return chunk address to 0x10. Similarly, when freeing memory back to the lookup assign list, it also aligns the chunk. The free routine aligns the first entry in the list. So what happens if a frame buffer that's not 0x10 byte aligned is placed into lookup assign list? Let's play the funky friend. Here we are using an alignment mask that gives us 8 bytes of padding. Then we set up the allocator to pre-allocate 4 frame buffer. The buffer will look like this one. Due to the padding, the buffer address will all end with 8. After that, the allocator gives us 4 buffers, A, B, C, and D, all of which have address ending in A. When these buffers are free, case release them one by one and insert them into the lookup assign list in order. First, we free frame buffer A. It gets inserted into the lookup assign list normally. Next, when we free B, the allocator first aligns the current header of the list, which is frame A. Then it sets the next point of frame B to point to this aligned frame A. And insert B at the head of the list. We continue by freeing frame C, which follows the same pattern. Finally, we free frame D. In the end, the lookup assign list will look like the layout shown in this diagram. Have you spotted this issue? This issue is in the next point of frame D. Due to misalignment, the next pointer points to the start of the pool chunk rather than the frame buffer. As shown in this diagram, you will notice that next point of frame D points to padding area, which stores padding size. When viewed as a 64-bit value, this pointer becomes something like 0xA and A0, which is an address in user space. Our plan is to allocate a memory page at 0xa and a0 to gain control of the list, and have the final node point to our target address. After that, when the device reads data, case will write the data into loss buffer. In theory, this gives us an arbitrary memory writing, right? However, we still face the same problem as before. We cannot control the content that we want to write. It also cannot use buffer mode in this case. At this point, we were stuck again. But after thinking it through one more time, we found another way. That abuses the local sign list again. As shown in this diagram, we first construct a fake linked list in user space. The address 0x414100 represents a user control memory address. Then allocate the frame buffer. It will align the trunk and update the list header. However, because the alignment logic treats the start of frame D as the next pointer. Once the first chunk is popped from the list, the linked list transforms into what you see in this diagram. Next, we allocate all the trunk from the local sign list. Then we trigger a stop to release all of the frame buffer. At this point, case start returning the buffer to the local sign list one by one. First, it will release the frame D. Then it will free the malicious chunk at 0xa and a0. After that, it frees the fake chunk at 0x414100. In the end, it will release our target address. As a result, the target address of the next pointer will point to 0x414100. In other words, we can write the address of our chunk into the target address. This value can be any user space address. That is, we now have arbitrary memory writing. We turn a useless bug into a powerful vulnerability. After we gain arbitrary memory writing on Windows 23H2, we can use any well-known technique to achieve EOP. Okay, let me demo it. The exploit is run on 23H2. I also use a normal user with webcam and allocate 4 frame buffer. And get system. Okay, next, let's talk about what else can be done with this attack surface and the bug class. This bug pattern may not only appear in kernel streaming. By paying closer attention to MDO-related issues, you might be able to discover many more bugs in other drivers. Takeaway: kernel streaming is a valuable research target, and likely still contain many vulnerabilities hidden inside. Understanding Windows API implementation and the layer misuse risk is key to find vulnerability and exploitation. Keeping this pattern in mind, it might be your next vulnerability. Thank you for listening.